All right, this video I'm going to talk you through the handout that is involving acceleration of free fall. We're really going to be dropping an object. So we're going to, if you read along with me, a rock drop from the top of a cliff, so from here, picks up speed as it falls, right? As it falls downward. It's going to be picking up speed here. So I'm just kind of highlighting this path here. Pretend that a speedometer and an odometer are attached to the rock to indicate the speed and distance. So a speedometer, like that in a car, measures the speed, and an odometer measures the distance at 1 second intervals. So both speed and distance are 0 at time 0, so at the top, right, when we drop it. So note that after falling 1 second, that the speed reading is 10 meters per second, which is what we see here, and the distance fallen is 5 meters. So we're going to be measuring here on the dial is going to be our speedometer, and this measurement here is going to be our odometer. So this is going to be a distance, and this is going to be a speed, where you have each of these tick marks are going to be 10 meter per second intervals. So here's 0, 10, 20, 30, 40, 50, 60, 70, 80, etc. The readings of succeeding seconds of fall are not shown and are left for you to complete, and that's what we'll be doing. So draw the position of the speedometer pointer and write in the correct odometer reading. So use G of 10 meters per second squared. Very key value here, that we will be using 10 meters per second squared. So we're going to say that objects that are accelerating towards the Earth are accelerating at 10 meters per second squared. So here's two equations. We're going to be saying that the instantaneous speed of fall from rest, that velocity is equal to gravity times time. So 10 meters per second squared times the time, number of seconds it fell. Or we're going to be using one of the two. We're going to be solving for, we're going to be using this equation here. D is equal to 1/2 gt squared, where 1/2 of, on Earth, right, gravity is 10 meters per second squared. I'm going to simplify this for you. So 1/2 of 10 is 5. So we're going to be using the equation, I'll simplify it as D is equal to 5t squared. So 5 times time squared. So let's do some of the numbers here. We're going to solve first. So let's apply these equations here. So the speedometer is going to be after falling 1 second. So the velocity is going to be g times t. So 10 times 1 second. The velocity is going to be 10 meters per second, and that's where this value comes in. So this is 0, here's 10. And then the distance is going to be 5t squared. Well, 1 second squared is 1 times 5 is 5, so the distance is going to be 5 meters. And that's your odometer reading there. So I'm gonna go a little faster here now that we're gonna be able, you can always go back and rewind this. So here, after 2 seconds, velocity is going to be gravity times time, so 10 times 2. The velocity after 2 seconds is going to be 20 meters per second. So here's 0, 10, and 20. I draw my speedometer here. And the distance traveled, D, is going to be 5t squared, where 2 seconds gets squared. So 2 squared is 4 times 5 is going to be 20 meters. This should be 20. Hopefully you can see that. After 3 seconds, velocity is going to be 10 times 3. Velocity is going to be 30 meters per second. So 0, 10, 20, 30. Here's my speedometer. And D is going to equal 5t squared. T, so is 3 squared is 9 times 5 is 45 meters. After 4 seconds, take a look. Keep looking through here. I'm still continuing to solve my speedometer and odometer. I have V is equal to G times T, so 10 times 4. The speed is going to be 40 meters per second. So 0, 10, 20, 30, 40. Bingo. There's my speedometer, 40 meters per second. And D is going to equal 5 times T squared, where 4 is my time. 4 squared is 16 times 5 is 80 meters. Next one, after 5 seconds, velocity or speed is going to be gravity times time. 10 times 5 is going to be 50 meters per second. So 0, 10, 20, 30, 40, 50. Here's my speedometer. My distance traveled is going to be 5 times t squared, 5 seconds squared. It's 25 times 5 is 125 meters. 125 meters for the odometer. And then last but never least, we'll do the last one here together, is going to be speed is g times t. It'll be 10 times 6, 10 meters per second squared times 6 seconds. Tells me it's going to be traveling at 60 meters per second. So 0, so 10, 20, 30, 40, 50, 60. Here's my speedometer reading. And my d is going to equal 5t squared. So in this case here, I have 6 squared is 36 times 5 should be 180 meters. So I've completed all these, and you can always go back and look and resolve these. But I tried to show you the math along here. So let's go through here. Let's answer these short answer questions. The speedometer reading increases the same amount, 10 meters per second each second. This increase in speed per second is called acceleration. And this is what we're looking at. The speed is changing, therefore it's increasing, therefore this would technically be a positive acceleration. The distance fallen increases as the square of the time. Right? If I look at this equation and put it down here, d equals 1/2 gt squared, where distance fallen increases at the square of the time. So if it takes 7 seconds to reach the ground, its speed at impact will be, well, v is equal to g times t. 10 times 7 is going to be 70 meters per second. The total distance fallen is going to be d equals 5t squared. 7 seconds squared. 7 squared is 49 times 5. Shows me that I get a total distance fallen of 245 meters. And its acceleration, this is a key. A lot of times people miss this. Its acceleration of fall just before impact is still 10 meters per second squared. So that concludes the first handout. Now let's do the second handout together. And this is falling and air resistance. So when I look at falling and air resistance, when I look at solving this one here, I want to make sure you realize what's going on here. Just like the picture before, you need to understand what's going on conceptually. We have this Bronco, this skydiver jumping out of this helicopter. And this individual is going to fall towards the earth. But things are going to start changing when I start opening this parachute. So here goes. Bronco skydives and parachutes from a stationary helicopter. Various stages of fall are shown in positions A through F. So A, B, C, D, E, and F. So using second law. So using this equation, A, acceleration equals the net force divided by mass. We can find that weight, really we're looking at weight, this is F of G downward, is what we're calling weight here, and F of AR upwards is what this example problem is calling R. So down is W and up is R. So let's look at this. That's the net force. We have two forces acting here. So let's solve. Let's do some of these. Find Bronco's acceleration at each position. Answer in the blanks to the right. You need to know that Bronco's mass is 100 kilograms, so his weight is a constant 1,000 newtons. Air resistance, R, varies with speed and cross-sectional area as shown. So we actually studied this, we just haven't called it this when we did our parachutes. So let's do the math first. So here I have 1,000 newtons. So notice, weight minus R, well there's no air resistance here, R is 0. So 1,000 divided by 100, right? So I have 1,000 newtons divided by 100 kilograms. Tells me my acceleration is 10 meters per second squared. The instant this individual Bronco jumps out. Well, notice as he continues to fall, air resistance increases. So 1,000 minus 400 is 600 newtons divided by 100 kilograms. Tells me that his acceleration is 6 meters per second squared. It's less. He's still speeding up, but he's speeding up at a smaller rate, so its acceleration is less. Still accelerating, but less than immediately upon jumping out, where here we would say this is free fall. Here, not so much, because the F of G, gravity isn't the only force acting on it, downward. So moving on. Letter C. If the downward force is equal to the upward force, I have 0 newtons of net force. The acceleration is 0 meters per second squared. We call this here, where he's falling, he's still falling towards the earth, but the forces are balanced. This would be a constant velocity. We would call this terminal velocity. We'll come back to that. And then he starts to deploy his parachute. And once you start deploying the parachute, things change. still falling downward, but he's going to fall down at a different rate. So here's what this looks like. If I take 1,000 minus 1,200, right, I'm still applying this equation here. I get, divided by 100, I get negative 200 newtons divided by 100. Its acceleration is negative 2 meters per second squared. In other words, he's still falling downward, but he's going to be slowing down. He's actually slowing down. The parachute is going to increase the resistance, the air resistance. And then here, I look at this problem, or this location, where I have 1,000 minus 2,000 divided by 100. Oh, that should be 100. So I have negative 1,000 divided by 100. Its acceleration is negative 10 meters per second squared. Meaning as soon as you deploy the parachute completely, this is going to slow down significantly more. And then last but never least, where we have air resistance and weight equal to one another, you have 0 newtons of net force, therefore your acceleration is 0 meters per second squared. So here, once again, has reached terminal velocity. So you want to go back and make sure you understand what's going on with the math. But now let's answer these analysis questions. When Bronco's speed is the least, or 0, right here being, his acceleration is the greatest, or the most. In which position does Bronco experience a downward acceleration? Well, let's see. Downward is going to be, we're looking at a downward acceleration. Downward here, boom, location A and location B. In which position does Bronco experience an upward acceleration? Well, that's going to be locations, where am I at here? Oh, D, negative, and E. Let's see, D and E. Yes, sir, or ma'am, or whoever's listening here. If anybody's listening. If not, oh well. Note number 4. When Bronco experiences an upward acceleration, his velocity is, boom, think of it this way. He's still falling downward. It's still downward. The velocity is still downward, even though he's slowing down, right? The parachute is changing the rate at which he's falling downward toward the earth. That's why parachutes make it safe. You slow your velocity way down. In which position is Bronco's velocity constant? Well, we've already labeled these. We've got location C. We also have location F. We call both of these terminal velocity. So in which position does Bronco experience the terminal velocity? Well, here my only options are C, or well, A, B, C, D, and E. But we could also say location F as well. So I can add those. In which position is terminal velocity the greatest? Well, okay, this is kind of missing something. That at location C, terminal velocity will be faster than. Notice, it slowed down to reach yet a second terminal velocity with the parachute deployed. So the terminal velocity when you're just a skydiver is when the net forces are 0. This is going to be much, much faster than this parachute deployed. But if Bronco were heavier, in other words, if I had a greater F of G downward, right, greater weight, the terminal velocity would be greater than as well. And there you have it, the 2 handouts that we looked at from class.